Okay, multiplying this term out, what do we have? We have x minus x naught equals 1/2 v naught t, 1/2 v naught t, plus 1/2 vt, 1/2 vt. Now, we already have found that v is equal to v naught plus at. So rather than v, I'm going to stick in v naught plus at. So we've got plus 1/2 v naught plus at, and then times t. And multiplying that out, we have 1/2 v naught t plus 1/2 v naught t plus 1/2 a t squared, 1/2 at squared. Well, the 1/2 v naught t and the 1/2 v naught t add together to give us v naught t plus 1/2 at squared. Let's take the x naught and stick it over on the other side and rewrite that equation, and let's see what we get. What we end up with is bringing the x naught over. We have x equals x naught plus v naught t plus 1/2 at squared, where, let's remember, x naught, this is the position at t equals 0. In other words, it's x evaluated at time equals 0. And v naught is the velocity at t equals 0. In other words, it's v evaluated at t equals 0. We can see that right from these equations. If we put, remember this is x as a function of t, if we put in 0, that's 0, that's 0, so all we get is x naught, x when t equals 0. What about here? Putting in t equals 0, t equals 0, that's 0, v of 0 is equal to v naught. So v naught is just the velocity at t equals 0. Well, what does this look like? Well, this x equals this x naught, v naught t, 1/2 at squared. Remember, a, v naught, and x naught are all constants. This is a function for x of t. Here's the functional dependence of t. What does that look like? Well, it looks like a parabola. What do these constants do to determine the shape of the parabola? Well, x naught, that's the value of x at t equals 0. So that is this constant right here, that value, that's x naught. V naught, that's the initial slope. So what is the slope of our graph here? The initial slope is v naught. So does the graph go up initially, or is it negative initially? Is the velocity negative? Is it flat initially? Whatever v naught is, that's going to tell us what the initial slope of our graph is. And then a, remember, that'll be the second derivative. That will tell us, does the slope go up very quickly from there? Does it go up more slowly from there? Is the parabola very, very steep, a very sharp parabola? Is it a much more slowly increasing parabola? Is it a downward facing parabola if a is negative? Whatever. So our values for x naught, v naught, and a, remember, this is not, we don't write a naught because a is just a constant. It's the same as t equals 0 as any other t. So it's just a constant. X naught, v naught, a, all constants. That's how those three quantities will affect the shape of the motion, the shape of the x versus t graph. What I'm going to do is I'm going to take one equation that I had written down before, and I'm going to derive one more equation so that we have a group of 4 equations that will describe what our motion looks like. We have that v equals v naught plus at, so I'm going to rearrange that and solve it for t. Let's bring the v naught over to the other side and make this v minus v naught, and divide by a, and what do we have? T equals v minus v naught over a. So we've solved this equation for t. I'm now going to take this result and put this into the second equation for t here and t here. So what do we get? We get x, I'm going to bring the x naught over here, x minus x naught equals v naught times v minus v naught over a, plus 1/2 a times t squared, which is v minus v naught over a squared. Now I'm going to simplify this a little bit. I'm going to multiply both sides by 2. So I'm going to take 2 times this. So 2 times that, and that's going to cancel my 1/2. And then notice I've got it divided by a, and I've got a divided by a squared, so I've got a over a squared. One of those cancels and leaves me with just one a in the denominator. So I'm going to multiply both sides by a. So I'm going to multiply this by a, and that will cancel that a, and then a squared. Which leaves us with 2a, x minus x naught is delta x, equals, now we're going to multiply all this out, 2v naught v minus 2v naught squared, plus, now I've got v minus v naught, and I'm going to square it. So v squared minus 2v naught plus v naught squared. Now what are we left with? Well, let's notice we've got 2v naught v minus 2v naught. Well, those are the same, so they cancel. We've got a v squared, so v squared, and then we've got v naught squared minus 2v naught squared, which leaves us with a minus v naught squared. Okay, there we go. Very good. Let's bring the v naught squared over to this side, and that will give us one more equation, v squared equals v naught squared plus 2a delta x. Let's write that one down, and we'll get one more equation. So what we're left with previously then is v squared equals v naught squared plus 2a, and rather than delta x, I'm going to leave it in terms of x minus x naught. That'll make it a little bit easier later on. We'll see why. Now let's remember we already wrote that delta x was equal to v average times delta t, and remember with delta x is x minus x naught, and v average we found was 1/2 v naught plus v, and delta t is equal to t. Bringing the x naught over, we have x equals x naught. Bringing the x naught over, x equals x naught plus 1/2 v naught plus v times t. There we go. This leaves us with 1, 2, 3, 4 equations. I'm going to write these down in a particular order, not because there's anything special about this order, but if we remember them in this order, I can easily refer back to them by, say, number. Equation 1, equation 2, equation 3. So let me write those down like that. So what we have is v equals v naught plus at. X equals x naught plus 1/2 v naught plus v times t. X equals x naught plus v naught t plus 1/2 at squared. And v squared equals v naught squared plus 2a x minus x naught. And I'm going to keep these, I'm always going to write them in the same order to just help us remember them. I'm going to refer to this one as equation number 1, this one as equation number 2, this one as equation number 3, and this one as equation number 4. Whew, that is a lot. What we're going to do next time is start with these 4 equations and use them to look at some different kinds of problems. Remember, all of these were derived with the assumption that we were looking at uniformly accelerated motion. So these will only apply for uniformly accelerated motion. But that's what we'll look at next time. We'll look at a number of different examples of uniformly accelerated motion and see how we can put these into use. See you next time.